What we're going to do together is take a look at these 4 equations and turn them into 4 tables and 4 graphs. And then once we've done that, we're going to look for some similarities and some differences. Let's start with the first column. This here is a list of x's. We're going to use the same x's for each of these different equations. And we're going to list the y's that come out of these equations at these different x's. So for example, if x is -3, put the -3 in here. 2 times -3 is -6, just like that. Would you, at this point, just do a quick pause? I want you to fill out the rest of this column and then unpause when you're ready to check. So on a paper or on a marker board, just get the rest of those y's. Okay, I hope that your numbers here are going to match mine. And then 2 times 1, 2 times 2, and 2 times 3. So we've got a table. Here it is. And we've got all these ordered pairs. Now I've already set up a Desmos. It's okay if you want to just follow along with mine, or if you want to open up a Desmos yourself and plot these points, that'd be okay too. But you'll see here we have the x's, and those are the points that we just found. They're all plotted. Now next up, I want you to notice an important difference in how this second equation is written. Notice here, it's 2 times the x. That's multiplication. You've been multiplying numbers for a number of years. This is now 2 to the power of x. And this is just a little trickier to evaluate. So let's take a look at this whole column together. I actually want to start here at the bottom with 2 to the power of 3. So I'm putting this 3 in where that x is. Now 2 to the power of 3 means 2 times 2 times 2. So 2 times 2 is 4, times 2 again. This is the number 8. When x is 2, we've got 2 to the second power. That's 2 times 2 for 4 overall. And then 2 to the first power. Any number to the first power means you have that number 1 time. So this is going to be just 2. Now, with what comes next, we're going to notice a pattern. All of our y values here are just going to be going down by 2 each time. But let's make sure we understand where that's coming from. So for 2 to the 0 power, if you remember the previous lesson, any number to the 0 power is always equal to 1. And it's for that reason. Each time I go down, I'm dividing, as the exponent goes down by 1, the output gets divided by 2, and 2 divided by 2 takes us to that 1. Now, as we continue up here, we're going to end up with fractions. That's what negative exponents do. They flip things upside down. So when you take a 2 and flip it upside down, it becomes a 2 in the denominator of a fraction. So 2 to the -1 is the same thing as 2 to the positive first power in the bottom of a fraction. Now we put a 1 on top because really, remember 2 is the number 2 over 1. We just don't write the over 1 because dividing by 1 doesn't change anything. But when you flip it, that 1 on top needs to be there to show that there's not just an empty numerator. Okay, let's simplify that then. 2 to the first is just 2, so this is 1/2, or 0.5. Next up, 2 to the -2 power, a negative exponent just flips upside down and becomes a positive exponent. So 1 over 2 to the second, which is 1 over 4, which is 0.25. And then 2 to the -3rd is just 1 over 2 to the positive third, which ends up being 1 over 8, or 0.125. Now I want you to continue this pattern in your mind. If we keep dividing by 2 each time you go down, as your exponents become more and more negative, your fractions are going to become very, very tiny. But it's important you know they're always going to be positive numbers. It's going to be 1 divided by some positive number all the time. Let's see how this looks then when we plot these points on a graph. Hey, So there in blue is our second set of ordered pairs. Notice that the shape is different. So this first set that we did, y equals 2x, that's just a straight line. But this second one, that's got some curvy funkiness to it. With that in mind, let's take a look at the entire graphs. So now there's nothing special about the ordered pairs we picked. These are just examples of points on the graph of the equation. So here in Desmos, I typed in y equals 2x. It's now showing us the entire line. If we turn on the second equation, so y equals 2 to the power of x, notice how different things look. It's got this curve to it. As you go backwards, as you go to the left, it looks like it kind of almost goes flat, because it kind of almost does go flat. And the numbers get very, very small. Take a look at those y values. They're super tiny. As you go to the right, though, the graph goes up, and it goes up very fast. This is an example of something we're going to call later on exponential growth. But straight line when it was 2 times x, curved graph when it was 2 to the power of x. Okay, let's go again here. Now in this third column, we're going to do the same thing. We're going to take these x's, put them in, and then simplify. I'm going to be very honest. I just recommend, see, notice how it's starting to get a little bit complicated. There's multiplication, there's addition. We'll do 1 or 2 of them the longer way, evaluating by hand, but then I'm just going to use the calculator to make my life easy. Let's start down here with a 3 in for the x. Or tell you what, let's start at the top. Let's put a -3 in for the x. So 2/3 times -3 plus 6, what comes out? 2/3 of -3 is -2 plus 6 is going to give us a 4. Now when you put a -2 in, here's where I'm going to recommend we start using the calculator, only because it doesn't come out evenly. 2/3 times -2 is -4/3. And -4/3 plus 6 is just a fraction. And there's nothing wrong with that, but I want to make sure that we get that right. So I'm going to open up here this new Desmos and do 2/3 times -2 plus 6. Okay, so it's about 4.6 repeating, which as a fraction, I'm going to write it, is 14/3. So to get that fraction, just go to the front circle, click it. That's how you can switch between fraction and decimal on your Desmos calculator. The same is true on the scientific calculator, by the way. So 14/3, which is about 4.7. Next up, let's put a -1 in for the x. Now, I'm going to not work too hard. I'm going to take my calculator here, just change the -2 to a -1. So it's 16/3, which as a decimal is about 5.3. Okay. So when x is -1 on this equation, y is 16/3, which is about 5.3. Next up, this one we can do probably without the calculator. Put a 0 in here. 2/3 times 0, any number times 0 is 0. Add 6, you should end up with 6. Let's just do a quick check. Put a 0 in for the x. 6 comes up. We're in good shape. All right. Why don't you also, on yours, finish up? I'll finish up mine. We'll check and make sure we get the same results. So a 1, a 2, and a 3. Put a 1. Two. Okay. And the 3. Now this one's going to come out evenly to an 8. Yeah. Now the reason I know this one's going to come out evenly is because when I put the 3 in, 2/3 times 3. The 3's, they undo each other. Divide by 3 times 3 just leaves the 2. The 2 plus the 6 is what gives us that 8. Now I want you to know a subtlety here. Notice on here I had an equal sign for the 4, but for these decimals, I'm using the little squiggly equal sign for the approximation. 20 over 3 is not the same number as 6.7. They're very close, but they are not the same thing. This is rounded a little bit. That's why you put in the little squiggly equal signs to show that you may be rounded a little bit. Okay, and let's take a look now at these on a graph. They look like this. So it's a line with a slope of 2/3 and a y-intercept of 6. The whole graph looks like this. So once again, a straight line. That straight line coming from the relationship where we're doing a multiplication. 2/3 times the x is what gives us that straight line pattern. Okay, now this last one. Here, I'm going to recommend that we just use the calculator the whole time. And the reason I say that is we could do this by hand. We've talked about negative exponents. We've talked about zero exponents. We've talked about multiplying fractions along the way. But it just takes a lot of time. So to save time, let's use that calculator and start filling some things in. Now, how you type this in matters. So going back here, I want to do 6 and then the parentheses, 2/3 in the parentheses. And now make sure you get an exponent. This is where we're going to put now our different numbers. So starting with -3. Okay, this comes out to 20.25 exactly. So that's 81/4, 20.25. So I'm going to write in here that this as a fraction is 81/4, and that's equal to 20.25. There was no rounding, so straight up normal equal sign. Next up, let's replace the -3 with a -2. Okay, so that's 27/2, which is 13.5. And again, it's equal. So 27/2 equals 13.5. No rounding, so straight equal signs. Now the -1. Ends up being 9. Now I do want to take just, oh, that's not the right one. I do want to take just a moment and see where that 9 comes from. So let's think over here off to the side. 2/3 to the -1 power. You got to remember what negative exponents do. Negative exponents flip things upside down. So a -1 exponent takes the 2/3, flips it upside down to become 3/2. And the exponent then becomes a +1. 3/2 to the power of 1, that's just 3/2. 6 times 3 is 18. 18 divided by 2 is where that 9 comes in. Next up, this one, we'll check it on the calculator, but we can also do this one in our heads. Let's think a little bit. 6 times 2/3 to the power of 0. I need you to remember that any number to the power of 0 is 1. So this really is the same thing as 6 times 1, which should be just 6. Let's check this out then. If I put a 0 up here, I should end up with a 6 in the end, which we do. Okay, let's keep going. Next up, 6 times 2/3 to the first. Now, 6 times 2/3 to the first should end up being 6 times 2, which is 12/3, should be 4. Let's see what happens. This exponent into a 1. Hey, there it is. So let's spot a pattern here. 20.25, 13.5, 9, 6, 4. Notice our numbers are going down. That's just a way to help us check ourselves because that pattern should continue. So our next number should be smaller, and then the last one smaller still. Let's go back, put a 2 in here. Okay, now notice this is a big old long decimal. So the fraction is 8/3. The decimal is approximately 2.7. So 8/3, which is approximately 2.7. I rounded, so I'm using the little squiggly approximation sign. And then lastly, Let's put in a 3 for that exponent. Okay, so 16/9, which is about 1.8. 16/9, which is about 1.8. Okay. So here's what I'm trying to drive home. I tried to make two equations that had some similar parts. They've got the same numbers in them, but notice that the numbers are put together differently. That has a big impact on the outputs. Let's see what this looks like graph-wise. So we saw this line with a slope of 2/3 and a y-intercept of 6. Here now is what our last function looked like, the 6 times 2/3 to the x. We turn on the whole equation, what we see is it's got this kind of curvy shape again. That's not a coincidence or an accident. That's actually an important feature. When the variable is up in the exponent, you are going to get graphs that look like these. These are called exponential graphs because the variable is in the exponent. When you have just regular old multiplications and additions, like we've been working with for years and years, that's what gives you lines. So let's summarize it this way. Here it is in words. Linear change, graphs of lines, occur when x is a multiplier. So that would mean it's just a number times x. Like here's an example we had of that. Exponential change, which is what this unit focuses on, is when your variable is an exponent, and those graphs have these curvy shapes. So I will expect you to be able to know, just by looking at these graphs, or these equations rather, that this is going to be a line, this is going to be a line, number times x, number times x. This is going to be a curve, exponent is x. This is going to be a curve because the exponent is x.